In this video, I'll be demonstrating how to align a diffraction grating in an external cavity diode laser, or ECDL. The ECDL consists of two cavities, one being the laser diode cavity, and the second being made up of the back mirror of the laser diode cavity and the diffraction grating. The second cavity is also referred to as the external cavity. For this demonstration, we have mounted a laser diode and a commercial mount that is both temperature and current controlled. We have also adjusted the outgoing lens such that the outgoing beam is collimated. Secondly, we have mounted the diffraction grating on a commercial mount that is adjustable in the horizontal and vertical angles. We have modified the commercial mount by attaching a mirror that faces the diffraction grating and moves along with the angle of the diffraction grating. When working with an open beam, and especially when introducing a new optical element, it is a good safety precaution to use glasses, because you'll never be 100% sure how the optical element will interact with the beam for the first time. Prior to this demonstration, we have calculated the horizontal angle needed for the diffraction grating, based on the laser diode frequency and the groove spacing of the diffraction grating. We have oriented our diffraction grating such that the grooves run vertically. When a diffraction grating is introduced into an oncoming beam, two important things happen. First, the beam is reflected off the diffraction grating, and then, in our case, reflected off this mirror and sent out of the system. This beam is referred to as the zero-order maximum. Secondly, the diffraction grating produces two first-order diffracted maxima, one in the outgoing direction and one in the backwards direction towards the laser diode. For this demonstration, we'll be using one of two geometries available for an ECDL, the Littrow geometry, the second being the Littman-Metcalfe geometry. In the Littrow geometry, we directly send the first-order maxima back into the laser diode such that we can tune the lasing frequency by adjusting the horizontal angle of the diffraction grating. The mirror that we have mounted facing the diffraction grating compensates for small changes in the angle of the diffraction grating and keeps the outgoing beam in relatively the same position. This setup is typical of many commercial products or laboratory setups, except for two major differences for demonstration purposes. First, our external cavity is much larger than needed. And secondly, we have mounted it on an optical table out in the open, where a commercial product would be enclosed and stabilized. For this demonstration, I'll be showing you how to adjust the angle of the diffraction grating such that the first order maxima goes directly back into the laser diode. The diffraction grating has 2 degrees of freedom in its angle, a horizontal and a vertical. Therefore, this procedure has two parts. First, adjusting 1 degree of freedom, and then secondly, adjusting the 2nd degree of freedom. The order that you choose, horizontal, then vertical, or vertical, then horizontal, does not matter. Now on to the first part. The first step in the first part is to locate the first order maxima. In our case, a diffraction grating is highly misaligned. Therefore, the first order maxima is easily located. But it may be the case that the diffraction grating is only slightly misaligned. In this case, the first order maxima will be indistinguishable from the beam exiting the laser diode. To solve this, you can purposefully misalign the diffraction grating within the tolerances of your system such that you can easily identify the first order maxima. I'm going to choose to start with the horizontal angle first. This means I'll be adjusting the horizontal angle such that the first order maxima is aligned vertically with the laser diode. Alternatively, if you choose to start with the vertical angle first, you will be adjusting it such that the first order maxima is aligned horizontally with the laser diode. Now I'm going to adjust the angle. Alright, so it looks pretty good now, and it's aligned vertically with the laser diode. Now I'm going to take the vertical angle and adjust it such that the first order maxima is closer to the laser diode. Alright, now that I'm closer, I can see that my vertical alignment is not as good as I thought, and I need to readjust the horizontal angle. There we go. Now it looks pretty good. Now I'm done adjusting the horizontal angle, and this degree of freedom is eliminated, and I no longer need to touch this knob. Now I'm going to adjust the vertical angle such that the first order maxima is overlapping with the beam exiting the laser diode, and I cannot distinguish between the two. Alright, so it looks like I'm there. Now I'm done with the first step, and I'm ready to proceed to the second step. Alright, now we're ready to proceed with part 2, the final adjustment of the final degree of freedom, in our case, the vertical angle. Since we have aligned the first order maxima such that it's just overlapping with the outgoing beam from the laser diode, and we can no longer distinguish between the two, we can no longer visually align it. This means we have to take advantage of a trick within the laser diode. If we turn the laser diode's current just below the lasing threshold, when we introduce the extra light from the first order maxima back into the laser diode, this extra light will cause it to start lasing, and there will be a noticeable difference in intensity in the outgoing beam. So the first step is to lower the current of the laser diode just below the lasing threshold. The laser diode spec sheet should state the lasing threshold current, but we can also inspect the outgoing beam. So I'm going to lower the current now. Lowering the current. There we go. Now it's no longer lasing. Let me show you that again. Raise the current, lasing. Now I'll lower the current, no longer lasing. There we go. Now the current's set such that the laser diode is just below the lasing threshold. Now I can proceed to adjust the vertical angle. Since the first order maxima is below the laser diode, I'm going to adjust the angle up. So I'm adjusting up. There we go. You see that? A slight increase in intensity, and I'm going to continue adjusting up. There we go. Now there's a dramatic increase in intensity. Now I'm going to continue adjusting up and misalign it. Alright, so now I'm going to adjust it back down and align it again. As you can see, it's no longer lasing. I'm starting to laze, and now it's reached a maximum intensity. Now the angle of our diffraction grating is set such that we're setting the first order maxima directly back into the laser diode. Now, if we adjust the horizontal angle, we can change the lasing frequency of the system. And now we'll analyze it with a spectrometer. Alright, we directed the outgoing beam into a spectrometer for analysis. Now, as you can see, as I change the horizontal angle of the diffraction grating, it changes the lasing frequency of the system. When I reach the end of the range, it jumps back to the natural lasing frequency of the diode. There we go, back to the lasing frequency of the diode. We have about 6 nanometers of range, which isn't too bad for this demonstration setup. This concludes our demonstration. I hope you found it useful and educational, and thank you for watching.